Hello community! Today we talk about something beautiful. Now in my last video we were talking about grokking LLMs. And we verified it for an arithmetic operation, modulo p, and for some complex arithmetic operation. And then I ask here my subscriber in the community tab, hey, should I show you the extreme power for your LLM or you want to go for perfect reasoning? And of the 223 votes of my subscriber, there's a clear majority for perfect reasoning. So here we go. So now we move into the question, hey, does grokking work also for human sentences? And here, since we want to go for reasoning, we go for the first step is detect hierarchical structures. Now, there's a beautiful paper by Stanford University and MIT. It is exactly 1 year ago, and they looked here into grokking for hierarchical structures. And if you look at the training dataset and the generalization dataset, you see, hey, that looks interesting. So, Stanford and MIT show here the ability of transformer model to comprehend and utilize here the hierarchical structure of sentences in natural language processing. And this research team introduced here the concept of a structural grokking, a phenomenon where transformers demonstrate an improved ability, up to 100%, to generalize hierarchically when trained extensively, far beyond the typical training duration, grokking from my part 1 video. So isn't that beautiful that transformers are capable of doing this? But of course, this goes against what we normally know, the previous assumption that transformer lack these capabilities. Stanford and MIT showed us, hey, this is not the correct assumption you have. And they showed us also that our models, our LLM, have to have a specific depth of layers. So it should not be too shallow in the architecture of the transformer and not too deep. So for the next step, I need a metric that is specific here for causal reasoning. And again, we have here a study from Stanford University and MIT, and this is about here the intrinsic compositionality in the transformer with tree projections. And here they found a new metric, and this metric is called a tree structuredness metric. And this is a crucial or critical indicator for recognizing when transformer achieve here the optimal depth for structural grokking. So this metric now measures how well a transformer internal computation on each layer on an input can be approximated with a tree-structured neural encoding, which correlates, of course, strongly with the hierarchical generalization that we are looking for. So we have a new metric, and this is exactly what we need for a tree-structured neural encoding. Now for my green grasshoppers, and I know that you are listening here, why do we need a tree? Well, a tree is important in our language because human languages are organized in a tree-like way, like words grouped together in phrases, which then group into larger structure. Then we have sentences and paragraphs and so on. So this tree structuredness metric checks if the transformer internal processes follow this tree-like organization, because then we have a perfect one-to-one match of an internal logical structure. It helps us to understand complex sentence structures, and we use this in language translation, in text generation, in answering complex questions, and in generating a coherent text for summarization. So you see, this tree structuredness metric is great. Now, we have now 3 elements. We have the time, and I showed you here with extended training. This emphasizes here the importance of a prolonged training period for achieving significant generalization capabilities in neural models that reach 100% for a development dataset. Then we talked about the optimal depth that we need for the transformer architecture to have a beautiful balance between an acceptable computational efficiency and this great performance in complex language tasks. And of course, we have to develop methodologies to evaluate the performance of the transformer, especially for the structural understanding, because my subscriber voted here for understanding. So now, in causal reasoning, the ability to infer relationship based on structural clues is really important. And now this is exactly why we start here. If we enter here the area of causal reasoning in the structural dimension. Just the sentences are hierarchically structured. Many forms of reasoning, including the causal reasoning, involve understanding here the hierarchical relationship between all the different elements in a sentence. So, in both the language understanding for translation and causal reasoning, for example, to recognize those dependencies is crucial. And this beautiful metric helps here the model to understand which part of a sentence depend on each other. And this is so important to understand the causal dependency when we want to achieve perfect reasoning. So here we have it. What have we achieved? Grokking works to detect hierarchical structures in human sentences, which can be further utilized for a better, almost unbelievable, close to a 100% causal reasoning performance with Grokking. And now we are finally there where you have been waiting. Here, Grok transformer are implicit reasoner. And you say, implicit? Is there something special about the implicity here? Yes, absolutely. And we will go to the edge of generalization, to the edge of what an LLM can learn. Ready, set, go. What I want to show you here at the end of this video, demonstrating that a fully Grok transformer can achieve near perfect accuracy on challenging reasoning tasks. And this underscores here the potential of the parametric memory in the transformer, the inherent memory that the transformer have been pre-trained on. And we will contrast this capability against the current limitation of state-of-the-art models that rely on non-parametric memory, where we have to retrieve and augment external data, external information, external knowledge, put it in our LLM, and those LLMs typically fail, those RAG systems fail to perform adequately under similar conditions. So we have now a competition. Hey, the Grok transformer versus RAG. And Grok transformer, they will amaze you. Let's have a deeper look. Grok transformer for reasoning. Okay, now it gets a little bit complicated. Highlighting here now the critical role that this extended training in achieving what is termed grokking, this is particularly important for the reasoning task that requires here the understanding and applying complex structured knowledge. And this extended training leads to a fundamental change within the transformer, within the neural network, within our tensor structure, how knowledge is encoded on each layer in the transformer architecture, and how it is manipulated within the transformer. And later in the video, I show you how we can optimize the internal connectivity of our classical transformer architecture. But let's start at the beginning. How to build the perfect grokked transformer. Beautiful. Now, MIT starts here with the classical transformer architecture. It is a GPT system, but not the latest Omni version, where we are not really aware of all the hidden optimization that Omni did. So they go with a classical GPT system. But of course, if we have a system and we start with our Grok training, then we need, of course, a perfectly aligned and optimized training dataset for our training. So training dataset are extremely important, and we need here, of course, the perfect dataset. Now, the first step is here, we look at the task that the system should do, and then we design here the perfect dataset for that particular task. So to study now the transformer ability to generalize, they constructed here, the authors of the study, a synthetic dataset that mix here some atomic facts and some inferred facts And this is so important because this mimics here a formal system of mathematical axioms and mathematical theorems, and therefore we are really able to provide a clean and controlled environment to test the model reasoning capabilities. Because, if I tell you the words, yes, nice, handsome, and beautiful, you might say, this sounds similar, no? But we do not want something similar. We want absolute precision. We have to have a formal system of axioms and theorems where it is clearly distinguishable. So therefore, we go here with atomic facts and inferred facts, deduced from the later one. Okay, and now they studied here to have a look into the black box. And they say, if we open up this black box that we call an LLM, how can we discover what goes on in a transformer if we want to analyze this generalization through Grokking? How does it happen here in the neural network architecture? And it was shown, and I will focus on this a little bit later on in 5 minutes, that there is a formation of specific pathways in the neural architecture. And the authors call this a generalizing circuit. So we follow here a specific pathway between the layers, and this particular patterns within our layers, they facilitate the learning process within the Grokking phase transformation. So those circuits that we will discover within our architecture represent a structured pathway that efficiently encodes and retrieves knowledge for reasoning tasks, but based on the parametric knowledge within the LLM, based on the pre-trained, and not that we need external RAG data. For my green grasshoppers, here you have it if a little bit more in detailed, but what I want to show you is whenever we find those circuits, these generalizing circuits, we understand how they form in the neural network gradually, occurring over extended training. This is what is grogging all about. This is so important that certain pathways within the neural network strengthen, forming those circuits which are crucial for the model to generalize its reasoning capability effectively. And now if we found those circuits, we can ask, what can we do to the architecture of our LLM to even improve on the performance of this LLM? And we will see in 10 minutes that memory sharing across specific layers in our architecture, or enhancing here the cross-layer connections, will help significantly in overcoming some limitation that still exist for specific tasks. So we will also cover here some new dynamic transformer architecture optimization for the perfect reasoning capabilities. Okay, so yeah. Data. We have in-domain, or domain-specific data, and not domain-specific data. Now here we go a step further. We have here, to test those LLMs, we have to design something like an out-of-distribution example. So those are examples where, let's think back about the fine-tuning of an LLM, the development dataset may differ significantly from the pre-training dataset, or the training dataset when you trained your LLM. So these out-of-distribution examples will become now very important for our grokked transformer. And they have a strong influence when a transformer will enter the phase transformation of grokked. And if you are a subscriber of this channel, you remember that about 2 weeks ago, I talked about here, if we fine-tune here our LLMs, and we have the training accuracy on our training data set, if we have known data in the fine-tuning data set, it is fast. It completely saturates at 100%. And overfitting, we know exactly on the development accuracy, and we say this is it. But if we have an early stop to prevent overfitting, our unknown data in the fine-tuning data set, they are only learned with an accuracy of below 20%. And you might ask, hey, this out of distribution, is this something like unknown training data from the video that you showed us about 2 weeks ago? Well, it is kind of similar, and we'll explain this in more detail. But for the moment, let's assume we have this perfect data set for training now our transformer to go into the phase transition and become a Grok transformer with a almost 100% reasoning capability. Now, if we have the data set and we have the architecture GPT system, we have to ask, so what is the test that we can run on a GPT to explore here the pathways inside the different layers of the transformer architecture? Now, we will focus here on 2 tasks. And the first task is the task of composition. What is it in detail for my little green grasshoppers? Let's say an LLM needs to chain different pieces of facts. The first sentence is Tony's wife is called Michelle. In the second sentence, Michelle is born in 1964. And now you want the LLM to come up with a compositional sentence that goes Tony's wife is born in 1964. However, the authors studied this and said, hey, this transformer-based language model, they can perform this implicit composition, but with a large amount of negative results are consistently reported. So this is not at all working really well. So they say, hey, there is a specific gap. This is a specific frequency at which the model knows under all the underlying basic facts, so sentence 1 and sentence 2, but fails to compose them. And this is why we started with structural knowledge, and we verified that this is happening in the Grokking phase transition. Because now we're going to look at this. Now, in the classical way, what we do to solve this problem, you know this, no? This is RAG. RAG solves everything. RAG is a miracle. And we use RAG to ground here our LLM with beautiful grounded information. So what we do, we extract now this information from an external source. Let's say it's a database. And in this SQL call, in this function calling, we get back, hey, Tony's wife was born in 1964. And we do not have to have this operation of composition from the sentence understanding. We just check the fact from an RAG system. But now we strive for causal reasoning near perfection. So what we do? Yes, we built a knowledge graph, a beautiful knowledge graph, and this is so great. So we generate a random graph, a random knowledge graph G. I have a multiple playlist on knowledge graphs, consist of our entities and of our relation, where each entity has 20 outgoing edges that connect through a random relation to other random entities. And the atomic facts are, of course, the edges, and those are the triplets in our graph. You remember, subject, relation, object, which we partition disjointingly into an atomic in distribution, into an atomic out of distribution array with a distribution of 95% to 5%. And now you remember when I talked to you about here knowledge graph, and we sit on a node and we hop on one hop, and we have 2 hops away. Now the rule for a 2-hop composition in our particular case is this simple rule. And we have here the notation that H is the head entity, B is the bridge entity, and T is the tail entity. Please have a look at my other videos about this. And with this knowledge graph, we are now able to build the perfect GPT test to explore here this particular task of composition of knowledge. And we use this knowledge graph now as our backbone. Let's have a look at the results. Now, the authors did this, and you remember I told you we have 2 different tasks, but I only told you about the first one we call composition. So we have a sentence 1, someone has a wife. Sentence 2, this wife was a name and was born at a specific date, and then you compose this together. Beautiful. Now let's look here at the y-axis, we have the accuracy, 100% top. And here we have this grokking here, the optimization step, when grokking sets in, and we want to see here the distribution. Now, again, you remember the training in domain, no, not in domain, but in distribution, I have to come up with the definition soon, is, yeah, we just jump up to 100%. You remember? Known data in distribution, yes, we have here the training accuracy goes up, yeah, beautiful, saturated 100%. So, beautiful. Training, check. Now, for the development, or here it is called the test dataset, the unseen data, where we expect the system to generalize and apply the found pattern to solve this problem, is now different. In green, you see grokking happens. Look, we come up to 100%, maybe 98% only, but it is happening. So grokking is taking place here, but only for the in-distribution dataset. Because if we look here at the same for the out-of-distribution dataset, so if you want here the completely unknown dataset, they stay flat. There's not this grokking happening, and we will investigate why. And this will give us some beautiful insight to further develop the theory. But of course, this was task 1, where it's not working. And yes, you guessed it, I have chosen now a different task where it is working. So we have here the training accuracy goes to 100%. The test accuracy of in-distribution data goes to 100%. And the test accuracy in blue of out-of-distribution also reaching, with grokking setting in here in the extended training phase at 100%. We have a perfect causal reasoning system for the specific task of the logical task of comparison. And you might say, hey, how is this possible? You have to explain this to me. And this is exactly what I thought, and I talked here to the publication, and I say, how is this possible? But yeah, I have to come up with this definition of OOD. You can read it, but OOD is not just unknown data in the sense that it is some random data set or an arbitrary data set that was not similar to the training data set, but it has, we designed it in a specific way. It was systematically designed to challenge here the model's ability to find out, is the model able to generalize to new knowledge or not, A or B. And this is the beauty. So OOD is, unknown plus the specifically designed characteristic to really be able to target here the LLM's ability to generalize and have a clear and a unique result of this. And atomic in-distribution data contains data similar to what the model was pre-trained on, and atomic out-of-distribution data consists data that the model was not pre-trained on, representing new combination or new types of data that were not present in the pre-training and training data set. You guessed it, no? So now come 2 important facts. The mixture of this atomic data to the inferred data that I told you for the perfect data set, this mixture is crucial. Imagine it is like if you have a machine, an engine, a car, and you have your petrol. And the mixture of this petrol is crucial for the performance of the engine. And here the same thing happens. This inferred to atomic ratio, we call it phi, is crucial for an effective grokking phase of our LLM. And a higher ratio tends to accelerate the grokking process. Reducing here the extended training requirements means it is cheaper. We do not have to pay as much for the computer infrastructure that runs for 100 of hours. So, phi has a significant influence here. And then, as I told you, the internal parametric memory function and the non-parametric memory. And I will show you that the result demonstrates that transformers with a fully grokked parametric memory outperform state-of-the-art LLMs that rely on a non-parametric memory for complex reasoning tasks, RAG, indicating here the potential that we have in our parametric memory from the pre-training of the LLM to handle large search spaces much more effectively. So those Grok transformer, they are something real special. Okay, so now that we have all the tools and all the elements, now we can start. And we say, hey, I told you, I want to open the black box of LLM. I want to look into each layer and find out what's happening. What does grokking really mean on a layer level? And here we have two forms here to perform our mechanistic analysis of this black box. And the first way, how to generate deep insight into the model's, LLM's, decision-making process is called logic lens. Very short for my green grasshoppers, this method interprets the activation within the transformer network to understand which part of the network are being used for specific reasoning tasks. And then we have a little bit more meta technology, a little bit more high-level technology. It's called causal tracing. Yes, we trace here certain pathway through all the different layers of an LLM. And this technique involves here that we perturb here the input and observe how the changes will affect the output of the system. And this here in particular helps us to map out those causal pathways within the neural network, showing us clearly which components are critical for some specific reasoning outcomes. So we can really identify the single tensors. Now let's have a look in detail at both methodologies, and we start with one with the logic lens. You can think of about 4 simple steps that you're gonna enjoy. Now the first step, of course, we extract the activations from all the specific layers within the transformers. And those activations refer, of course, for my green grasshoppers, to the output values of the neurons before they are passed through an activation function. Now, those activations are then transformed into our famous logits. This is normally done by multiplying the activations with the output embedding matrix. And the output embedding matrix is essentially a learned representation of each word of our vocabulary and is used to convert the high-dimensional representation of the model into a specific score for each word in the vocabulary. You know this is classical stuff. Now, you remember from my video where I talked about logits, those logits represent the unnormalized logarithmic probabilities that the input corresponds to each possible output word in the model's vocabulary. You know this from attention mechanism. And now, by examining this logit, the researcher in the study interpreted what the model considers most likely before it applies the softmax function to derive now the actual probability densities. So, by comparing now the logit across different inputs, or to manipulate those inputs slightly, such as changing the word, or better is you add some noise distribution. Now the researcher can see how sensitive the model output are to those changes that we inflicted on the system, on very specific parts of the system in the input. And this provides you some insight into what features the model is paying attention to. But this is more like pinpointing here exactly. Like a flashlight with a focus light here on a spot in the black box of our LLM. Yeah, an example for my green grasshoppers. But this causal tracing now, the second methodology, this gives us more an overall image of what's inside this black box. So, let's start here. We want to understand what are causal pathways and how we can find them. At first, we have a normal run of the system. So, this LLM processes the input normally and the activations of interest. Everything is recorded. And this set of activations serves here as a baseline for us. And then we have a certain slight perturbation that we introduce in the input. Altering a word in a sentence, adding noise, whatever you want to do, image, word, it works generally. And the model is running again with this perturbed input, and the new activations are recorded all over. Now, the activations from the normal, the perturbed runs are compared to identify the changes. This is called an intervention. An intervention is then performed where the activations from the perturbed input replace those in the normal one at a very specific point or specific layer, and the rest of the model's computations are executed as normal. You see what we do? And the final output of the model is then analyzed to see how this intervention affects the outcome. Now, we record here the change in the output, and this gives us a measure of the causal influence of the perturbed component in the system. And we do this for everything in this black box. So this is the way how we can map out now those causal pathways within the neural network. And this shows us which components are now important, maybe even critical, for some specific reasoning outcomes. And the authors of the study did this in detail. Now, look here, analyzing the inner workings of an LLM throughout Grokking. Remember, we're in this very specific phase, and the task is composition. So, as I told you, we have first the normal run. In all the different layers, we look at this, beautiful, then we have a perturbed run. And then we have this famous intervention. And we look what changes when we apply this intervention in the system. And we measure the change and we try to understand what is happening to the overall performance. If you want to understand this on an even more detailed level, please read this publication. It is really a great read if you're interested. Now, for my green grasshoppers, here's a simple example to understand causal tracing on a more higher level. But what is important? You know, we have now a second discovery within this month. You remember this video of about 2 weeks ago, 2.5 weeks ago, where I told you, hey, there's a new discovery in AI research that we found within the black box of an LLM. In the neural network, we found heads, and they are specific heads that do the retrieval for the LLM. And you guessed it, they're called retrieval heads in the specific layers of our LLM. So if we have AI agents and RAG system where we have the retrieval, augmentation, and generation, so for the retrieval, we find out that only 5% of all the heads that are available for this task are doing actually the retrieval task of R, of RAG. And now we find some critical pathways. And they call this here generalizing circuits. But those generalizing circuits within our neural network, within our transform architecture, are just the causal computational pathway that are calculated in the Grokking phase transform. Isn't this beautiful? So, with these two possibilities, we can probe here the black box, our LLM, and we can map out here the causal pathways within the neural network, showing us which components are critical for the specific reasoning outcomes. So within 1 month, we discovered 2 new facts. We have retrieval heads that are so important for RAG, and for causal reasoning, there are specific circuits within the neural network that do all the work in the Grokking phase transition. Beautiful. Now, if you want to read the original literature, this is a screenshot for the original study. Please read it. Or maybe you prefer here my way of explaining this, where we start with the training of an LLM. And you know, at first, beautiful, the system only memorizes here specific training examples at the very beginning. And they also found that those memorization is happening also in specific circuits in our neural network architecture. And they call those circuits that are only memorizing the solution to an example, memorizing circuits. But the more training is happening, the more epochs we train, we fine-tune our model, for example, we have a phase transition. And over time, with enough training iterations, much more than errorless stopping or overfitting, you know, what we have found in part 1 of this Grokking video. This LLM now develops what is known as generalizing circuits. Those circuits capture here the underlying rules or the underlying patterns in the data much more efficiently, and they are responsible for then close to a 100% reasoning capability of our grokked transformer. Now, this grokking, there are factors that influence the performance of grokking, the speed of grokking, and so on. And I just want to show you 4 factors. The first, you know, this is this ratio from inferred to atomic in distribution, for example. Then we will look at the number of layers in this transformer, GPT. Then we will see that there is a performance tuning that we can do with some memory sharing, and the training data set I already mentioned to you. So let's start with the number of layers in a transformer. So the authors did the following. They built different LLMs. The first LLM had 8 layers. The next LLM they built had 24 layers. And then they built an LLM with 36 layers. And they said, so how does grokking change if we build here different LLMs with different numbers of layers? And you see here for the training data, yes, immediately we jump up to 100%. So beautiful, we have saturation. But then for the test or development data set, we have this what's happening. Look at the green one. This is now the test or the development accuracy on in-distribution data in this data set. So for an 8-layer LLM, this grokking takes place, it starts very slowly. So, okay, so we increase to 24 layers, and 24 layers, look at the performance. Yippee, this is it. Just 30,000 optimization steps. But if we go now to 36 layers, and this is this green line with triangles here, we are much faster approaching here our 100% performance threshold. So you see, the number of layers in a Grok transformer have some impact on the grokking phase itself. Now, you noticed, let's go back, here my phi was 9. Here's my phi 18 and phi 5. So they played around and say, what is the impact of phi, of this ratio, to the performance of grokking, the performance of grokking phase transition? And here's the result of the research. And now we do this for all data points and in distribution data here. So this inferred atomic ratio phi correlates with generalization speed. Now look at the ratio. Now let's say we go with 3. This here is the performance curve of 3. That's not famous at all. Blue is 5. Blue is a little bit better. 7 looks nice. Green is 9. Yep. 12 or 13 is here our dark orange brown one. And 18, if phi is 18, you see, that's a nice performance. So you see, phi correlates significantly with the generalization speed. But there was another insight I would like to show you, that the authors found that normally you would say here for the training or the fine-tuning here, that also the pure data set size is important, no? Let's go with trillion, no 10 trillion, 100 trillion token in the training data set. And this was the old belief that the data set size is important for the accuracy of the model. Now, closer inspection shows us, no, this is not the way. What is crucial is the data distribution. This means, in our case here, the ratio phi of inferred to atomic data. Not the pure size, because you can have a lot of garbage, and you know this garbage in, garbage out relation, this works here also. So size is not what matters. If you just copy the complete internet, and let's say maybe only 20% of the internet is not really that high intellectual stuff, you know? So the size does not matter, but the quality of the data set, this data distribution in our specific data set for the grokking phase to happen, this is the actual deciding factor behind grokking and the generalization for causal reasoning. Beautiful. Now, Short interrupt, short break, yes, new idea. You remember, if you are a subscriber of this channel, that I had this video about in-context learning ICL Plus and it outperforms fine-tuning in RAG systems. And here I showed you something like this. If we have really not just a few shot example, but a many shot example, let's say 3,000 examples in my in-context learning prompt, that even if we go with the orange, the random ICL data, they start slow, but the more examples I have in context, you see it also comes up to 90-something%. And at specific time, it even outperforms here the fine-tuned here with the green triangle. And you would need more compute resources in fine-tuning to come up to the performance here of many-shot examples. And we notice, and I showed you in this video, the more many-shot example you provide to the LLM, the better it is and the higher this saturation level is. So this system, ICL Plus, does not stop at a certain threshold. Look at here, threshold is above 90%. So you might ask, hey, is there a correlation between this many-shot example in ICL Plus to what you just showed us on grokked transformer and the grokked phase transition phase? Well, if you do a PhD in computer science or mathematics, wouldn't that be a beautiful topic? Okay, let's come back to the main part of the video. So, we have run a set of causal tracing and logic lens experiments across all the different model chatbots throughout all the training parameters. So what we discover? We discovered that in our neural network architecture, we find here in the Grokking phase generalizing circuits. These causal computational pathways after the Grokking happens, and we are now in the Grokking phase, and they become detectable for logic lens and causal tracing. So this means within our architecture of the transformer, we now locate a highly, and now this beauty of interpretable causal graph structure within the transformer architecture for our specific causal reasoning task. So now the black box opens up. Now we really can look into all the different layers, how they interact for specific tasks. But of course, whenever something is not working, and I showed you that for composition, the OOD, the blue line, it stays almost at 0. So this OOD generalization does not work for composition. But it did work for comparison. So why doesn't it not work for composition? What is the main insight into the model? What happens there? Now, we have these two elements to look inside the black box and to explain here the deficiency in OOD generalization for the task of composition. And now the authors noticed doing all these experiments, while the model does acquire here this compositionality throughout the Grokking, it does not have any incentive to store the atomic facts in the upper layers of our architecture. They do not appear as the second hop during training. And the authors argue that this fact explains why the LLM in general fails in the OOD setting, where those facts are only observed in the atomic form, not in the compositional form. And this is because they argue the OOD atomic facts are simply not stored in the upper layers of our architecture when they're occurring during the second hop. So you might say, hey, if I now know why the system is not working, I can take actions. I can make it better. I can, for example, here have the idea that proper cross-layer memory sharing mechanisms for my transformer architecture are needed to improve here the OOD generalization that does not work for the composition task. And you are not gonna believe it, the authors did exactly that. They said, okay, we take a very old model. You see here on the right hand side, they took the universal transformer from the very early day of the transformer architecture. You know, when we had here the recurrent encoder block and we had the recurrent decoder block. You know, GPT is only a decoder, but if you go with the complete universal transformer, they just did this, and they said they allowed the model to share the knowledge in the upper and the lower layers, and for some specific E and for some specific data. And if you share the parameters on the first 4 layers and on the last 4 layers, you get this. Look at this. So in green, we have our in-distribution development or test data set. Yeah, beautiful system is perfectly doing of grokking and great. Look at the scale. But now, remember, the OOD test or development data set that was flat all the time. Now look at this. Now grokking starts to happen also here. So you see, we can optimize our classical transform architecture, our classical GPT structure, just by enabling here the knowledge sharing in the lower 4 layers and in the upper 4 layers, and then even our OOD data will have the phenomenon of grokking and can achieve a much higher accuracy in causal reasoning. Isn't this beautiful? Isn't this amazing? From something that was not working, having here the tools to open the black box, analyze here the internal combustion system that's going on here, tune it and find out what to do, you can have here an unbelievable performance jump in your transformer. Okay, I think this is the end of part 2. I hope you enjoyed it. And yes, of course, there's an outlook for the next part. Because you remember we just did composition as a task. But I told you there's another task, a task 2, for comparison, where the grokking works out of the box perfectly. Now we're going to analyze why this is happening. We're going to use here our logic lens and our causal pathway analysis to have a deep dive in the architecture and understand why comparison is happening out of the box. Plus, in part number 3, finally we will compare here the fully grokked GPT system, and we compare it to a GPT-4 turbo system with the perfect RAG system. And what it was a Gemini 1.5 Pro with the perfect RAG system. And we give it reasoning tasks. We look at the performance of a grokked GPT system to the latest and best RAG optimized system. And we will see who is winning this comparison and how you can have this effect with your open source transform architecture, with your vision language model or your large language model. But this will all happen in part 3 of this video. I hope you enjoyed it. I hope I see you in the next part.